Hi, welcome back to Physics 210, Chapter 2. Now we look at the example of static equilibrium. Okay, we start with number 1. Oh, sorry, this is number 2 already. Okay, number 2. So let's assume there is an object. Okay, there's an object. This one will be extremely easy. So we start with something with a mass of, let's say, 5 kilogram. All right, the mass of 5 kilogram, and it is hung from a string, inelastic string. Okay, so that's it. Okay, a mass is hung from the ceiling by a string. Okay, by a string. Okay, by a string. Calculate the tension in the string. Okay, calculate the tension in the string. Well, this is an easy one. Okay, now first thing we do is we label all the forces that we know. Okay, we label all the forces that we know. So starting from the object itself, right, and the string. Now you can forget about the ceiling there. Now this object has a weight of W equal to mg, and because it is in static equilibrium, so we assume that the tension is T. Okay, we assume the tension is T. Now how do we solve this? So first we have to apply the condition. What are the condition? Well, the condition will be something like this. Because it is in static equilibrium, okay, since the object is in static equilibrium, so the total force in this case, vertical force, is equal to 0. Okay, the vertical force is equal to 0. So that means the T, because going up is positive, right, minus mg is equal to 0. So your T is equal to mg. So which is equal to, so it is 5 multiplied by 9.81. Okay, so it is 49. Okay, 49 Newton. Alright, 49 Newton. So you see, you already actually used this type of concept before. This one is just one of the example, the easiest available. Okay, now next one. Example number 2b. Let's start with something a little bit more difficult. Now we want to have an object, okay, hung from the ceiling, but now by 2 string. Okay, so let's say the object is here. So you pull it sideways, and then it is like that. Okay, so you are given angle. This one, the angle here, let's say, is 60 degree, and this one is perpendicular. So this point here is called A. This point here is called B, so they can refer to them. Okay, now the mass of the object is, let's say, 10.0 kilogram. All right, so the question is calculate the tensions in both strings. Okay, tension in both string. Now tension in both string, that means there will be 2 here. One is the one at the top, so the tension is pulling up, so I will call this one T1. And the one that pulls sideways, going to the right hand side, I will call this one T2. Alright, and of course we have weight. It is W is equal to mg. Okay, W equal to mg. So now we need to form equation because there are too many unknowns, 1 and 2. Okay, 1 and 2. So first we know that W is equal to mg. Okay, and then we know one more thing. Okay, we know one more thing. T1 can be split into 2 components, right? You can actually split T1 into 2 components. Okay, this is your T1, and you can split it into 2 perpendicular component to each other. Okay, so this and this one. So I'll call this one TY and this one TX. And the angle here is 60. It's the same here, 60. Okay, so this one 60. So from here you can calculate the tension. Your TY is equal to T1 sine 60 and TX is T1 cosine 60, right? Okay, now we know that, okay, it is in equilibrium, right? Okay, assume in equilibrium. So in equilibrium, the total vertical forces must equal to 0. So we start from here first. Okay, the total vertical forces will be equal to 0. So now we have this one. We start from here. Vertical forces, this one, Ty and W. So the Ty, okay, the Ty minus W must equal to 0. So Ty is T1 sine 60 minus W equal to 0, or you can move the W over here, it becomes mg, right? So that is our first equation. The first equation, you can actually calculate, there you calculate, or you can actually later replace them, okay, replace them. So next one is your T1 cosine 60 and T2, they actually balance each other, okay? So that means the total horizontal forces must equal to 0 as well. So I will assume that the one go to the right hand side is positive, so I have T2 minus the TX, okay, is equal to 0. So your T2 minus TX is T1 cosine 60 is equal to 0, or your T2 is equal to T1 cosine 60. Okay, so we have two equations. Solve that. Okay, we have equation number 1 and number 2. Solve it. We're going to get what? We can actually divide them. For example, number 1 divide number 2. T1 sine cos 60 divided by T1 cosine. You got tangent. Tangent 60 is equal to mg minus T2. Okay, mg minus T2. So the T2 is mg tangent 60. Okay, let's calculate what do we have here. Mg, the mass is 10 kg times 9.81. Okay, and then divide by this tangent 60. Okay, so we have 56.6 Newton, right? 56.6 Newton. And then from T1, from number 1, what is the T1? We can calculate from here actually. T1 is equal to 10 times 9.81 divided by sine 60. Okay, 113. Okay, 113 Newton. Alright, 113 Newton. Alright, so that is our example 2b. Okay, example 2b. Alright. Now you see so far we only involve the total force is equal to 0, right? Okay, the next one we're going to involve a little bit on torque. Okay, a little bit on torque or the moment here. So we go to page number what is this one? Number 5, number 4. So I will put this one back to number 2. Sorry, this is page number 2, yeah? Okay, so now we go to page number 3. Okay, so example 2C. Okay, example 2C, that is page number 3. To see, we will have a question that involve a plank, okay? A plank or a piece of wood supported by 2 points. Okay, supported by 2 points. So we start one here. Okay, one right at the end. Okay, one right at the end. And then another one somewhere here. They at a certain distance, of course. Huh? Okay, so there's a flow. Okay, so this one is a support A. This is a support B. Okay, so we assume that the plane is uniform, so the center of mass will be at the center. Now another thing is the length, the wooden PQ, the wooden plank is PQ. So given that the length PQ is equal to, let's say, 10 meter, okay, 10 meter long, and the mass PQ is 80 kilogram, okay, 80 kilogram. So there is a mass. So now the question is, if the plank, the wooden plank PQ is uniform, okay, is uniform, find the reactions on A and B. Okay, find the reaction on A and B. So that is our question. And this one definitely involve a few more concepts other than the total force is equal to 0. Yeah. Now the first thing we do is we redraw the whole thing. Okay, we redraw the whole thing. Oh, one more thing forgotten to give you. The BQ length. And the length BQ here, from here to here, is 2 meter. Okay, is 2 meter. That one you need. Without that you cannot do anything. Okay, so we have this here, support at point A. And then our point B here. Okay, so first, this is what we label the CG point. Okay, the center of gravity, and then the length here, each of the lengths. Okay, the length from here to the CG point, the length from here B to the CG point, and this one already given. So the total length of the wooden plank is 10 meter, and this one is already given 2 meter. So that means here must be 3 meter, and here must be 5 meter. Alright. So that is the first labeling about the geometry of the wood itself. The next one is forces. Okay. So the first thing we have is the weight here. This is a weight, W equal to mg. Okay, W equal to mg, and then we have two reactions. One from point A, one from point B. So I call this one RA, and this one is the RB. So there will be no more forces involved. Okay, no other forces here. So now you got two unknowns. Okay, two unknowns, and there is only vertical forces involved, no sideways forces, so you cannot take component. So that means you using total vertical force is equal to 0 does not bring you anywhere. You cannot solve it. So you have to at least solve one of the RA or RB. See or not? Okay, so what do you do here? So you can form equation first. So in equilibrium, okay, in equilibrium, the total vertical force must equal to 0. That one we know already, right? So we form the equation RA plus RB is equal to mg. Well, that is our first equation, but nothing much we can do because RA, RB both unknown. Okay, RA, RB both unknown. So now we just leave it like that first. Now we need a second condition. The total torque, okay, is equal to 0 at any chosen point. So when you choose a point so that to calculate your torque, it must be strategic point. You can choose a point here, or you can choose a point here. You can also choose a point here, okay? But you end up having two more equation, one more equation with RA, RB, and that one actually can, not to say cannot, but you are actually having more difficulty in solving the equation. So you can also choose somewhere here, okay? But it's not advisable to choose some other places that you don't have the physical distance known to you. Okay, you might say that, okay, what if I choose somewhere in the center here? Can, no problem, but you're looking for trouble in calculating the rest of the distance. Okay, anywhere can be used, but try to be strategic. I would prefer to choose point A or B. Okay, A or B. So let's say we take moment at A. Okay, and total torque must equal to 0. So now you redraw that thing, but you can actually simplify it rather than using one whole plane like that. Now this is the point A. Okay, the point A. You are taking moment around point A, so any forces that pass through A you don't have to consider anymore. So now leaving you with only two forces. Okay, one is the weight, another one is the reaction RB. Okay, weight and RB, both are 90 degree. Okay, and the distance is, well, distance here is what? This one is 5 meter, and this one will be 5 meter. All right, so see, remember taking torque or not? Well, taking torque, you need to consider which torque is positive, which torque is negative, right? So this torque, this force here is going to rotate the thing anti-clockwise, so positive torque. So this one is going to give you a positive torque, and this one will be a negative torque. Okay, so we come to this side here. Now the condition is already given. Total torque must equal to 0. Okay, the total torque must equal to 0, and it is a total of the positive and the total of the negative torque must equal to 0. You can calculate one by one, or you can put in straight away here. Our torque formula is R cross F, right? R cross F. We'll start with the positive torque here. The R is the 8. Okay, so this one is RB. So R cross F, but our F is RB. So this one you use RB. Okay, here. And then minus this one, negative torque here. This one is going to cause negative torque, so it's RW cross W equal to 0. So put in the equation. So you have RB, big RB, sine theta RB equal to, this one will move over to the other side, RW, W, and sine theta W. So now RB, you already know, RB is 8. Okay, this one 1. Okay, this one is sine 90 equal to 1. RW is 5 meter, and the W is mg. And this one is also sine 90 degree. So both become 1. You can simplify your equation, become RB is equal to 5 over 8 mg. Okay, we calculate that. The mass is 80 kg times 9.81. Okay, and then multiply by 5 and divide by 8. So you have 491 Newton. Okay, 491 Newton. Alright, so there is the first one. Okay, there is the first one. Now, the next force will be this one. Okay, from number 1. Okay, from equation 1, we can calculate RA. RA is equal to mg minus RB. So your mg, of course, you already know, right? Just now you can calculate. So now we use this one to calculate here. So mg 80 times 9.81, okay, minus 490.5. Okay, we use a more accurate one. So we have 294 Newton. Okay, 294 Newton. So you see, that is how we get the answer for this type of question. Okay. All right. Next example will be consider ladder leans against wall. Okay, ladder leans against wall. So that one is number D. Okay, that one is number D. So let's assume we have this. Okay, so slightly bigger, and these are wall. No friction on the wall, but the floor has friction. So we put a ladder something like somewhere like that. Okay, and the angle of the ladder is 60 degree, and the wall with the floor is 90 degree, and the coefficient of friction on the floor is equal to 0.62. Normal cement, 0.62, right? The mu value between the object in contact. Okay, now this ladder here, I'll call this one here is A and this one is B. So the length of the ladder will be 6 meter and the weight of the ladder is about 25 kilogram. Okay, so the question is calculate the reaction. Okay, calculate the reaction, okay, at A and B. Right, calculate the reaction at A and B. So we assume that the ladder is uniform. So first thing we do is we label all the necessary geometry. For example, the first one, this is our CG point. Okay, the CG point, and the length will be 3 meter, 3 meter. Okay, and then after that is all the forces. This is the weight equal to mg, and then this is a reaction from the wall. So this one is RB, and then there's a reaction on the floor. This one is RA. But don't forget, the wall is smooth, the floor is not smooth. So if the ladder, let's imagine both sides here, the wall and the floor got no friction, the ladder will tend to slide outward, right? The ladder will slide outward. So the friction is actually to maintain the ladder from sliding outward. So the friction must be pointing inward. That is a small capital letter F. Alright, so that is our diagram, right? That's the diagram. You give me diagram, I give you marks. Alright, then the next thing, we need to calculate form equation. Well, form how many equation? You can form as many as possible if you want. So in equilibrium, this is our answer already. Okay, in equilibrium, the total horizontal forces must equal to 0. Okay, so I see two horizontal forces here. So that means RB is on the left hand side, so it's a negative. F minus RB is equal to 0, so the F is equal to RB. Okay, equation number 1 cannot solve. Okay, but we actually know F formula for F, right? And next one is the total vertical forces must equal to 0. Alright, that's the first condition. Second condition, total vertical forces is W and RA. So the RA minus W is equal to 0. So the RA is equal to mg. Right? RA is equal to mg. You can calculate RA, but you cannot get RB, right? You cannot get RB. So how to get RB? Our RB, okay. Oh, sorry. This question here, I don't want to give you the mu value. I want you to calculate the mu value. Okay, I want you to calculate the mu value. Calculate the reaction at A and B and mu value. All right. So add in something extra. Okay. Calculate the reaction at A and B and mu value. Okay. Now, we already are able to calculate RA. So our RA is equal to the mass. Okay, the mass which is 25 kilogram times 9.81. So that one is our RA, 25 times 9.81. So I have 245 newtons. Okay, 245 newtons. Okay, and then our RB. Okay, our RB from number 1. Our RB is equal to F, which is equal to mu n. Okay, mu n. And that n in that case is a RA. Okay, that case, this is an n. So this one is RA. So the mu unknown, right? Mu unknown. So that means you cannot solve. Okay, you cannot solve. So you need to calculate. So your RB, see or not? Your RB is equal to 245 mu. Cannot solve. So this one will be equation number 3. Okay. So you have two unknowns now, RB and mu. You don't know, so you cannot calculate. So we need to use another another method now, because you already use total Fx equal to 0, total Fy equal to 0, right? The next one is the total torque must equal to 0. So we assume we take moment at point A. Okay, at point A, so that these two forces is not involved, right? So after that, you need to draw a simplified diagram to show all the forces involved. Okay, this is our flow. So this one is 60 degree. So now we have this wet W, and then we have this reaction. This one is RB. And you need to know the angle also, because later on you're going to draw all the displacement vector. So this one is a displacement vector, another displacement vector here. This one is RW, this one is RB. They are vector, yeah? And remember, the angle is important. This one is 60, so 30 here, so here must be 150 degree. This one is zigzag, 60, 60, so here is 120, alright? The angle is important when you calculate torque. Now, in equilibrium again, so the total here is equal to 0. Okay, the total torque must equal to 0. And then we use the point A. So the total torque is equal to 0. The total positive torque and the total negative torque must equal to 0. Now, RB is going to have positive torque, W negative torque. Okay, start from here first. So that one is RB cross big RB, and then minus the negative torque, which is the RW cross W equal to 0. So we can calculate RB from here, see or not? So this one is RB, okay, sine 120. The angle must be within that two vector, yeah? And then it's equal to RW mg, the weight of the ladder, mg, and then sine 150. Alright. Okay, after that you can put in the value and see what do we have for the answer. Okay, our RB now. Okay, RB here is this length, which is 6 meter. So 6 RB, and then our sine 120, sine 20, we got this one, multiply by RB. Okay, that one later, we can put this one in later. Sine 120 is equal to RW is half, right? So 3 mg, the m is 25 kg, 9.81, and sine 150. Okay, so from here everything we calculate straight, eh? 3 times 25 times 9.81 times sine 150. Okay, you got this. Divide by 6 and then divide by sine 120. Alright, so answer is the RB is equal to 70.8 Newton. Okay, 70.8 Newton. Alright, now you already have RB and you have this mu value. So since RB is equal to 245, okay, 245 mu equal to 70.8, so you can get your mu value. So we have 70 divided by 245, okay, 0.289. That is our mu value. Okay, you study friction in physics 110. Okay, so don't forget about that. Alright, so these are the example for our physics 210 chapter number 2 examples. Okay, there can be more than this type of example, yeah. Okay, so wait for the tutorial.